Welcome to the 14th video of this course on quantum processing. This course is divided into two categories, as I mentioned earlier in my videos, in the quantum information science part, and we did the last couples of videos on the quantum information theory, the general purpose to do quantum computation. Today is an introduction to the quantum simulation category of this course by reviewing some atomic physics background, some quantum optics that are necessary to build our understanding of quantum simulation. So let's first begin with our interest in the field of physics, the field of atomic physics, low energy physics actually, that we deal with the field, we deal with light, we deal with interaction between radiation and matter. In the classical picture we just have the classical dipole, the Hertz dipole, the plus and minus, the positive and negative for the Coulomb interaction between electrons, between protons, between the nucleus. And if I couple that with the light field, I produce just simple interaction between light electric field that oscillates back and forth with the polarization vector here and cosine omega t as a light oscillation, electric field oscillation. So the other picture, that the main interest of this quantum mechanics course and this whole course on quantum optics is that we do quantize atom into two levels, which is called the two-level atom picture. The two-level atom picture is that you have the ground state of your system. It's also a harmonic oscillator. This is a harmonic oscillator that you can have. And between the ground state and excited state, you have the omega, the frequency that can just a mismatch, can be the mismatch between the ground state and excited state energy. And if I couple that to light, now light is quantized. So I have photons with a specific momentum, for example. Okay. And if I do like to write down the Hamiltonian for, remember the Hamiltonian for describing the dynamics of the system, I can write down the Hamiltonian for the atom, the atomic Hamiltonian, as H as operator is H bar omega, some operators that can raise the degree of freedom of the atom into another degree of freedom, can destroy and create. So remember, so let me just put a reminder here of these annihilation and creation operators. If I have, for example, operator like this guy, this is the so-known ladder operator for creation and eigenstate for creation degree of freedom, that I can operate on some atomic system. Here just maybe you say whatever, this kind of atomic system or a harmonic oscillator for the light field for photons. So you can destroy, you can create, here you can destroy, here you can create. The creation operator will accompany the eigenstates for the n. So let's say that this is just mode k that we will see here. So this is nk, but here just n plus 1, okay, the square roots, and here you create n plus 1 for the eigenvector here. Here you destroy, so the destruction operator will be in terms of the eigenvalues, eigenstates for nk for the mode of the harmonic oscillator, and here is just the destruction operator. So remember that I can have a specific or well-defined number of photons, for example, by measuring or by recalling the number operator. The number operator acting on the eigenstates will produce number of photons for my eigen problem here, eigenstate problem here. This is the number state. So for our systems, the quantum systems, I can recall that the sigmas are for the destruction and the or the annihilation and creation operators for the atom, for the atomic systems. I can couple that with the light, which is the harmonic oscillation for light, h bar omega here for to 1. So this is the ground, this is the from the excited state, from the ground state to the excited state, and vice versa. And here AA for the destruction and creation. So the creation follows, or the destruction operator follows the creation. So this is what I call the dressed atom picture. So the dressed atom, that you dress your light field, which is a quantized version of photons, on the harmonic oscillation, or the harmonic oscillator for the atoms. So you can attach to each, so both attach both for the atoms and the light, that they are both harmonic oscillators for specific or whatever kind of degrees of freedom that you have. So for modes of light that you have, for example, mode K, you attach a harmonic oscillator to the modes with its characteristic polarization vector. So you can have different harmonic oscillators, different modes for light and also for atoms. So now you have full quantization picture of light and atoms, and they are coupled together. So let's take a look at the time evolution when we start to evolve our quantum system. So let's just remind ourselves with the ansatz of the Schrödinger equation, time evolution here. You can find that if I write down the time-dependent Schrödinger equation, time evolution of a quantum system here, psi, and I have the Hamiltonian corresponding to the atomic Hamiltonian, and if I couple light, I start to make some kind of interaction between the light field and the atomic systems. I can write down the H as both the atomic eigenstates, the atomic Hamiltonian, and also the light field Hamiltonian that's driving the system. Here the atomic Hamiltonian, and we have the energy as the eigenstates of your system here. You have the energy eigenstates for the atoms, and if I would like to write down the operator of the Hamiltonian by the dipole operator, I just have the electric field, or the dipole operator times the electric field operator. Now it's an operator because here the full quantized version. We have also the energy, the Zeeman is called Zeeman energy. This is a classical perspective of the coupling the magnetic field part of the light with the magnetic moment for the charges that we have in our matter. This is a classical, just a classical point of view, but it also can be a quantum if I just operate that by flipping the vectors for operators. If you look to solve a state vector that evolves over time, and this state vector is a ket operator by some coefficients, so those coefficients govern the dynamics of the system, in the grounded state and the excited state, it can be written like this way. So if you look at the, I just put 1 corresponding to the ground and 2 to the excited, but the eigenvectors here are just the ground and the excited states. I try to solve that, getting a differential equation that looks like this. So the time derivative, the time evolution of this state of the dynamics can be written like this. We have sinusoidal oscillation by omega t, and I'd like just to recall that this part is what we call the Rabi frequency. This equation is written to introduce you to the Rabi frequency oscillation, that's just this expression here. So the Rabi frequency in terms of the H bar, and here we have the dipole sigma, so the dipole matrix elements for the ground state and the excited states times the electric field that we have coupled to the system, coupled to the atomic systems. We can write down the dipole operator, the dipole matrix elements in terms of the ground state and the excited state. So it can drive the atomic excitation from the ground to the excited state by this way. So it can be written in 3 coordinates x, y, and z, and for the polarization components also in the terms of the x, y, and z for those dipole operator representation in matrix elements. So let me write down also the state vector representation here, the coupled differential equation that I mentioned, and I write down again the coefficients for the dynamics in terms of so just this is just expressed from this guy here, just expanding cosinusoidal oscillation by Euler, and then you will find the system looks like this for this differential equation. The exponential that you have, both exponentials here, you find that omega minus and omega plus. You have minus and plus. And actually this differential equation just parts of C1, so you have C1 and C2, but just write down this just for one equation. But you have to make sure that the plus and minus are well adjusted. For the interaction between radiation and matter, you notice that if your exactly frequency of the light matches the frequency of the oscillation of your atomic system, it means that you are on resonance. You are on resonance with a light field. So all the frequency of the light is exactly printed on the atom. If it's exactly imprinted on the atom with no kind of off resonance, then you can neglect this term. This term because it's very fast oscillation of the light field, and you can replace this omega minus omega here for omega the light, the frequency of the light, and omega ground excited means the frequency between, or the matching or mismatching between the frequency of the grounded state and the excited state of your atomic eigenstates. So on resonance, we can write down this like this. Okay, and recall this is just omega minus omega. We replace it by some expression here called the detuning for this nice detuning. Detuning means that if your grounded states and your excited states are of the atom, the mismatch or the difference between the grounded state and the excited state of the atom corresponds to the same for the on resonance case for light. It means that there is no detuning, but you can play with this detuning and play and create a lot of physics phenomena that we will encounter in this course actually. If you do that, so this is called the rotating wave approximation. Rotating wave approximation for the on resonance case that you neglect this term here. So the Rabi frequency actually, if you have detuning, then we can write what we call the generalized Rabi frequency. The generalized case for Rabi frequency. Which is equivalent to the Rabi frequency square plus the detuning square. If it's just no detuning, there's nothing else can be done, so the frequency is exactly the Rabi frequency. So let's see when light couples with atom with the detuning and the absence of detuning, or what we said, the detuning is zero, so the same on resonance case as I told you. It works like this. If you have the frequency of light matches the resonance frequency of the atom, then you have the whole probability to get to the excited state is 1. Okay? And this probability you can extract it by just squaring the modulus of the coefficients. If you just square the modulus of the coefficients for each system, sorry, here, yeah, square the modulus of the coefficient here, you find that it's a probability to get to the excited state. This is the case where the detuning is 0, and this is the case when there is detuning. Let's say, for example, it's 5 omega, whatever, this kind of detuning that you have. So you lower the oscillation, you lower the probability to get to the excited state. That's why the probability here decreases. Those equations are just the rotating wave approximation for atom, here for atom, and here for light. Look carefully at this. It's just a difference that the just expression for the omega for the light and for the atom. And here delta for the coefficients here is just for the specialized for the light. Okay, it's just the light for the coefficient for light in the ground state and for the excited state of this harmonic oscillator of light, which is coupled to the harmonic oscillator of the atom. So this is the rotating wave for atom, and this is the rotating wave for light. So just let me write down this delta coefficient here for the light. They are for the ground, they are the cosine Rabi frequency t over 2, and here is we have I as a complex sine for Rabi frequency 2 over 2, and this is on top of the fast light field oscillation of our light field that we couple to the atomic system. So let me take this and refer to another important thing here, which is the quantum evolution of our quantum system. So the quantum evolution of our quantum system, if I have a ground state which is spin down, for example, h bar over 2 plus or minus, h bar over 2 plus or minus for the ground state, and the excited state of our spin system, let's take a spin system, and I would like to flip this spin going from the ground state to the excited state. So let's recall the Bloch sphere. I introduced the Bloch sphere on the first part of the videos in this course. If you do not remember the Bloch sphere, just go back and check it out. And I also, when I intentionally mentioned the Bloch vectors before, I did that for this reason, that we will now explore the oscillation in terms of Bloch vector component, which oscillates around the Bloch sphere here. So u, v, and w, now our Bloch vector. And if I have the atom in the excited state and in the ground state, I can write down, for example, the atom in the ground state to be like this: Bloch vector 0, 0, minus 1. And I can write for w 0, 0, and 1 for the excited state. So the excitation around time, if I have the atom or the spin in the ground state and I start to make what I call pulses, I inject pulses in the system by light, just laser light. So if I inject a pulse which is pi over 2, I call it pi over 2 here, and I will introduce this pulse again here, and another pi over 2, and another pi over 2, and another pi over 2. Each pi over 2 corresponds to put the system in the superposition state. So if I would like to flip the spin completely to the excited state, I do what we call pi pulse over time. So let's take examples for these excitations. If I go from the ground state to the excited state, as I said, I apply pi pulse. Some for both. If I go from the ground state here to the ground state again, so it means that I did nothing to the system, but actually I did excitation. I did move the Bloch vector to go in the excited state, and then coming back, and then coming back, and this, all of these are just number of integers for the 2 pi pulses. It can be 4, it can be whatever. 4 pi pulses can be used for getting this spin in the ground state again after the evolution. So what if I get the ground state into the coherent superposition? This is very important. Coherent superposition of the ground and the excited state. It means that it lies on the sphere, on this plane of u and v, in the xy plane. And this can be done by just pi over 2 pulse. Okay. One thing to remind you with is that if I would like to calculate the angle of excitation around this Bloch vector, you just sum for the or get the integral for the this Rabi frequency, this frequency of excitation around this time window that you take to oscillate here. This is phi, and you can do that by even looking at the areas, the rectangle pulses of these pi pulses or pi over 2 pulses of light injected on the atomic system. So let's refer to another important thing here, which is another topic for this. Okay, let me cover this. Okay, so another important topic that I would like to introduce in this video is the orbital and spin angular momentum. We know for any electronic configuration for a system, atomic system, we can build it like this: 1s, 2s, 2p, 3s, 3p, and then 3d just over this for some energy. But let's write down some important, not only just orbital angular momenta, but also spin angular momenta here. So I don't only do kind of 1s, 2s, but I also add some J, which is the, we call it Russell-Sunder coupling. You can Google, just spin orbit, maybe just spin an orbital angular momentum into spin orbit coupling. So spin orbit coupling is a fancy as an exciting topic to talk about, but let's just base it to the ground state of our topic here, that we can electronically configure our electronic systems to be written like this. If I have a spin, for example, in this configuration, this is spin 1/2 system, but this is 2, so it means that I have half, which is 1, so I can write it like this. This is spin. And this is for the S and P and D and F and J coupling both. So this is states are examples of this. 3 means that I have 2s plus 1. It means that I have s, which is 1 here. For the 1/2, it means that for s, because it's 1/2, okay, just is j, s plus l is l. So half means that I have s is equal to, actually in the L representation, it's L is equal, ML is equal to 0, or L is equal to 0. So 0 plus 1/2 or one eigenstate or one eigen system for the spin is just about 1/2. Another configuration, which is 2p 3/2, and another configuration that you can build here.